the Astronomical Observatory in 2001, and from 2004 to 2011, he was also director of the Padova Astronomical Observatory, and finally he also was a member of the board and also vice president of INAF. Today, Enrico will talk about supernovae in multi-messenger. So you can start.
Oh, thank you very much for the invitation. It's a pleasure to be here. I don't come often, but I always want to come because it's a very nice place, and I have friends here, so it's a pleasure to be here. I try to give you an idea. I mean, you know that I officially retired 3 weeks ago. So I'm sorry for you, but when you retire, you look back and you think what you have done or what you have learned in your career. And so in my presentation, we will see possibly more a story of what happened or a result, or let me say, I always look to what comes next. So I also hope to give you some hint of where we can go in the future. So supernova in the multi-messenger era, for when you talk about supernova, any talk you will need first to say which types, okay? And there is this basic supernova type plots where you have that the classification of supernova is based on the spectra at the near maximum, let's say, and there is a division, you know, type 1 without hydrogen and type 2 with hydrogen. Then at some point we discovered that type 1 are more complicated than that. So no hydrogen is not enough. You have either there is a silicon line that make type 1a, or you have a helium line, type 1b, or there is nor silicon nor helium, and sometimes you have strong oxygen, which makes a type 1c. The point is that this division in type 1 and type 2 is misleading, because if you look 10 months after explosion, the spectra of type 1a and compared with all the other show significant difference. Type 1a shows strong iron forbidden lines, and the other shows calcium, oxygen, and if type 2, hydrogen. So our idea is now is that the first type 1a are for a thermonuclear explosion, and while the other types are all for core collapse of a massive star. All these types are powered by radioactive decay, and the difference between type 2, 1b, 1c is a progressive amount of ejecta stripping. The type 2 retain all hydrogen, type 1b lose almost all hydrogen, and type 1c also the helium envelope. This was the basic. Now, what happens in the last years? But first, I show this plot, which is the number of supernovae and the candidate supernovae in 10-year cadence, you see, in the last year. First of all, it is important to know which are the actors. There are the wide-field full sky searches. Zwicky transient factor is one of the major players. These are the fraction of supernovae discovered, I think, a couple of years ago by the different survey. And if you look to the number here, you see the number of supernovae increased by a factor of 100. When I began to work, there was 1 supernova per month where we had to work, and now we have a few per day. And it's also important to notice that we are losing, we cannot classify all the supernova discovered, and you see the number of supernova discovered in 2007, we almost make for all classification. These were the candidates, these were the classification, the one recognized. Today, we have about 10 times more candidates than classified supernova. And that was why we, a few years ago, 10 years ago almost, we decided it was time to invest in some instrument to do spectroscopic classification. This instrument for Italy is SOX. INAF is putting a lot of money in this instrument. We will go identity. It will be operational early next year. But this is another story. So what happens when we have all these new discoveries? And so we started, let's say, from here. It is a different way to look to the transients, where you have a plot of peak luminosity, absolute magnitude, versus characteristic time of evolution. And you see the position of extragalactic supernovae. Here you have the core collapse and the thermonuclear. As we all know, the thermonuclear are much more homogeneous than the core collapse. These are the region. So what happens with the new searches? This is what happens. The plot is pulled with the different kind of sources. And the reason is that we have a wider and deeper search, of course, so we have more statistics, we go deeper. And this is the reason we find fainter sources. But also what changes the cadence range. So the searches are both looking to more rapidly varying transient and more slowly varying transients. And this makes for the fast and for the superluminous supernovae. Superluminous supernovae is very strange. We are not discovered for many years why they are the more bright object, transient object. The reason is that, first of all, they are very rare. Second, the time scale of evolution is so long, months or even sometimes years, that the people did not recognize they were changing. So we need a long time scale to recognize them. But also important is the selection criteria for the transient. You see here, for instance, the position of tidal disruption event. They, of course, they are disruption of stars which orbit close to the black hole, in the massive black hole, for instance, in the center of the galaxy. The problem is that when you see a variability of, say, a black hole region, you suppose that it is a AGN, not a supernova. So in the past, search for supernovae were discharging transient occurring in the nucleus of bright nucleus, because say, well, that is not related to supernova, is something else, AGN variability. And removing the selection criterion and look into this object was discovered the tidal disruption. So I compiled a list of what I think are the today important supernova topics. And the list is very long. And the important thing is that each class is associated to some fundamental class of sources which we would like to know more. For instance, superluminous supernovae are probably the best candidate to produce magnetar, strongly magnetic neutron star. We have found outburst precursor of, so the core collapse, and there are months or few years before explosion, there is an outburst of the object which was found, which is yet to be understood in terms of stellar evolution. Why there are these things very close to the explosion? And other things, for instance, fast blue optical transient, very popular now. They are probably due to fall back to black hole or to newly formed black hole, or possibly to jets. I put with a different color tidal disruption event and kilonovae. The people usually say tidal disruption or kilonovae. Kilonovae are the merging of binary neutron star, all you know. Are they supernovae? Well, it is a matter of definition, of course, but they are as bright as supernovae. They have a time scale of evolution which is similar. They have produced new fresh nucleosynthesis. So, and they are the end of stars, let's say, because they are disrupted. So, well, they could possibly qualify as supernovae in this respect. Anyway, I will focus now on only two of these topics. If I hope, first, more detail on the first. I hope I'm not sure I will get enough of the second because of time. And I keep for second because you have Leonardo here working on these things, so you will have other chance in case to hear about strongly interacting supernova. But let's see, let's hope that you can do. So first things is I'm dealing with the progenitor of type 1a supernova, and the work was done for many years with Maria Teresa Botticella, Laura Greggio, and more recently with Vincenzo Petrecca in Naples. Start from this plot. I did this is a Hubble diagram with supernovae, which I compiled a couple of years ago, all the known supernovae, let's say, which shows that supernovae are excellent standard candle. You see they cover a range from 0, let's say, to over 1 in redshift. There is no other distance indicator that can cover such range with such precision. What we learn from this is better seen below. You have a deviation from uniformly expanding universe, which was interpreted, some times ago as a dark energy, something which is accelerating, which makes in supernovae, distant supernovae to go faster than the linear prediction of the Hubble flow. And this is the difference, you see. And it looks quite convincing that this difference is so. This is the best plot, the best fit that we have now with the cosmological lambda 0.7. And the line below is assuming the lambda, the omega lambda was instead 0. This is the difference that we are, which provide us with the evidence for dark energy. More recently, came a second problem, which is the so-called Hubble tension. And you see what it means, Hubble tension here. You see that the fit of the Hubble diagram, with all the data, provide a Hubble contrast of 73.2, something like this. While CMB, the Hubble constant derived for cosmology, the CMB background, gives 67.7. And I mean, you see the difference between the two here. As you see, there is some dispersion here, so one may be convinced that there is a difference, but we can possibly look better. In this plot, there's a recent compilation by Licia Verde that shows the evolution of the value of the Hubble constant as a function of time and the different measurement and the methods. So you have a CFIDS here and CMB. And you see that when the error became smaller for the two diverge. And the difference is now claimed at 7, 8 sigma. So this significance. It's important to notice that there are measures in between. Also one which was made with many of you by Nandita Ketan using surface brightness fluctuation, which is, it has admittedly a large error, but is in between. So I'm not completely sure what is the problem here, but suppose that you believe to the Hubble tension. Suppose you believe that this difference is real. What that means? Well, if you take the side of cosmology, the problem is if you talk with the cosmologist, it will say there is no way we can keep the standard cosmological model and have this Hubble constant. And if we really want to fit in, we need to change many assumptions of the model, which will be destroyed, and things that are the basic of our cosmological study, like the homogeneity, the isotropy, or change the law of gravity. So are very, it would be critical things to change. Let me say, my reply is yes, maybe. But we do not know what is dark energy. We do not know what is inflation. We do not know what is dark matter. So there are so many things that we don't have explanation in the cosmological model. I would be not so conclusive that we can keep the existing cosmological model. But anyway, I believe that anyone needs to look to his home and say, well, let's suppose instead that the problem, let's see if we can have a problem from the supernova side. So can there be systematics in the supernova sample which make this discrepancy, which can explain the discrepancy? So there can be systematic errors, and all the ones we came to mind to people were tested with empirical measurement. Say, measure supernovae here at a redshift 1, measure supernovae here in late type galaxy, early type galaxies, if there are differences. The test do not confirm the possible presence of systematic error, but the problem is we still do not know what are the progenitor systems for type 1a, and that is embarrassing after many years of work. So I start, as I said, from my very early work. In 1988, me and Massimo make first estimate of the supernova rate in the local universe. And we found that you see here in this plot, this is the supernova rate. Here there are the morphological type of the galaxy. The one on top are core collapse supernovae. The one below are type 1a supernovae. And what happened, what you can see is that type 1a supernovae, different from type 2, are in all type of galaxy, also in elliptical, where you have only old stellar population. While, sorry, at the same time, however, the rate of type 1a in star-forming galaxy is higher than in passive system. So you have type 1a supernova both in young and old stellar population. You need to have a star which explode, which have no hydrogen, because we don't see hydrogen. We have no compact remnant. And the idea coming that the progenitor must be evolved, slowly evolved star, like the one which produce white dwarf, that some way they reach the Chandrasekhar mass and then start exploding. I don't know, go in detail, is a debate which lasted 30 years, so please, I will select some topic. But from the beginning, there were two possible channels to make, how you make that the white dwarf grows above the Chandrasekhar limit. How you can do that? Either you transfer mass from a nearby star, less evolved, which grows, reach the Roche lobe, transfer mass to the binary. The binary, in some conditions, slowly grows, reach a limit, explode. Or you have two white dwarfs, which orbit one around the other, emit a gravitational wave, and so the system loses energy. They get closer, closer, closer. At some point, they merge, and then you have they grow above the limit. We have argument in favor of one channel, argument in favor of the other. Someone is also saying maybe the both are working, but I will address this issue only looking from the point of view of statistics. So from the point of view of statistics, there are two problems. Let's say there is one problem for white dwarfs which then favor this one, which is called single degenerate. One star is a degenerate white dwarf, the other is a usual giant. In this case, the problem is for white dwarf is that there was searches of binary white dwarf systems with the proper mass of range and the orbital period, and not many were found. Actually, no one really so convincing. So where are these white dwarf systems which are supposed to follow this channel? And that's favor the other. More recently, I would say that there were other arguments based on the so-called time, delay time distribution. What is the delay time distribution? Is the time from the formation of the system to the explosion. And these times depends on how the two stars evolve, and you can, and we go more deeper later, you can infer what system possibly is that produced the supernova. Again, some times ago, 10 years ago, 10 years later, our first estimates, the people began measuring the cosmic star formation history. There was a famous plot, was called at the time Madao plot, where you have a plot of star formation rate as a function of redshift, and it is this line more or less up here, which was derived at the time. And there was a paper, but there were many papers the same year, but let's say I took this one at the time. This was a presentation which I did in Antofagasta in 1988, and they showed this plot. They show that by measuring the supernova rate as a function of redshift, you can possibly confine the delay time from explosion, from formation to explosion. You see here is a delay time of 3 giga-year, and you will have this line. Here is a delay time of much less, 1 or 0.3 giga-year, and will follow this line. The measurement at time were this still, so no observational limit. So I decided we want to do something here. I try to fill this gap, this plot, and see if we can find that evidence. And this means that we started first the program in 1998, was the ISO and the wide field imager. Then we got involved in building a new instrument. The problem is that you need a wide field imager to find many supernovae. There were no instruments available at the time, so we got involved in building an instrument, which is now working, named Omega Gamma, the VST. The programs are very tiring, and that comes from the name. The first program was named the Stress, and the second was named Sudare. And Maria Teresa is very clever to find an acronym that make the point. So we start doing this. Now, we were so good, clearly, that we convinced the people which was something to do. And in 2004, confirmed in 2010, people was doing a search of supernovae with the Hubble Space Telescope, published a paper making a very strange claim, strange for all the people working in the field. So they plotted this, which is rate supernovae as a function of redshift. You see the point, and you see some line. The problem is that they say to fit the point, which is this full line here, you need to assume a very narrow delay time distribution, which means that you have a 4 giga-year from formation to explosion. They found this result, and they confirmed it a few years later. The problems. If you look, as I already told you, the rate of supernovae in young stellar population is higher than in passive stellar population. See, in another way, this is a plot of the supernova rate per unit mass as a function of the color of the galaxy, where in this side, there are, it correlate with age. So here you have a young stellar population, here you have old. If you take this model, this assumption, let's say, of the delay time distribution, and you see the prediction, these are the observations, these are the predictions. You have a shortage of supernovae, but which is a factor 10, is a logarithmic scale, in young stellar system. You cannot have the supernova that you see in young stellar system with this delay time distribution. So Mannucci published a paper and say, well, yes, maybe we have two components. This is the same only with the logarithmic scale, so it's the same plot over here, but with the addition of a fast channel. You say possibly there are two channels for producing this system. One, the one shown by Strolger, slow, and one very fast, producing these things. My problem with all these two is that they don't make any reference to the stellar evolution, which should say something at some point. And also that, yes, these models explain very well the rate in galaxy. You see here are the observation and the model with this delay time distribution, but actually do not really explain the Strolger data. You see, the prediction will be this, why there seems to be a point out there. So we say, let's start from another with Laura Reggio, we say, let's start from another point of view. Let's try to derive some constraints to the late time distribution based on what we know of the stellar evolution, which is a lot. So if you do that, and there are also, I must say, a lot of uncertainties. So not let's fix on one case, but let's assume different possibility and see what come out. So we say there are some limits which are cannot be avoided. If you want to have a white dwarf, you need to evolve, let's say, an 8 solar mass star. You need to have the time from the 8 solar mass formation to becoming a white dwarf. This is not long. Cosmological term is 100 million years or something like that, but you need this time. Then a second point is when, a second break is when the mass of the star, the white dwarf that you are producing, becomes too low. So if it becomes too low, you cannot reach the white dwarf will be low mass, and you cannot, it is not possible to take that up to the Chandrasekhar limit, because if you start in a system which is 0.2 masses, the two solars, the two white dwarf, you merge them, it make 0.4, will not explode. So you need, there is a limit, let's say it's 2 solar masses, stars with a mass below this do not make a massive enough white dwarf. And then you have also a problem with the secondary. I said 1, but it should be, oh, sorry, it should be written 1. If the secondary star is too low mass, it will take forever before getting to evolve, and will not contribute in a useful within an ample time. Using these constraints, some guess on the distribution mass ratio of the two stars for single degenerate. And a distribution, the other uncertainty is the distribution of separation of the stars at formation and after all the common envelope things what happens. There are many uncertainties there. So Laura say, let's forget this. Take two systems, one which is born distant and one which is born close. They are the DD, double degenerate close, double degenerate wide. So we have these three, say, prediction for different model. We can check that with the observation and see if someone is favored. And this is the result of many years of work of many people. Our point are this red one. And you see two things. First, there is a problem with the measurement of Stroger. Not only that the point at high redshift is a bit low, but not that severe because the error bar is very large. But also the point at mid redshift are very high compared with the others. And this is more of a problem because here you have a good statistics of this. Here you have possibly 1 or 2 supernovae. Here you have 20 or 40. So there is this problem. Anyway, at this point, given all the others, passing the line that we can predict inside for the evolution with redshift of the rate, you see that, well, there is not that much difference between the model. It's difficult to distinguish. Possibly we can only, well, we can certainly exclude the narrow long delay time, this one. We can possibly also exclude the double degenerate wide system. So if they are double degenerate systems, their distance distribution must be relatively small. However, conclusion is that, I quote here, the dispersion of the measurement is comparable to the scatter of theoretical track, and therefore it is not possible to disentangle among the two different progenitor scenarios from the rate as a function of redshift. And so we went back and say, okay, but what happens if instead of looking to the overall cosmic rate, we go to look to the individual galaxy? What we need to do for that point? So we need to do a prediction, we need to know what is the star formation history of each galaxy, okay, in the sample. This can be done. There are models which are used in cosmology where there is different prediction, but what we did with Laura is we adopted a parametrization for the star formation history, is this plot here. We adopted a single star population. We come from different models of the single star population and construct and constrain this model using known properties of galaxy in some well-observed sample. For instance, the cosmos deep field. Here is a two-color diagram for galaxy in the cosmos deep field. And these are the predicted color of this galaxy based on this star formation history, okay, and the single stellar population known. Okay, we made a lot of tests, but we say, well, okay, we are satisfied that we are able to reproduce the spread which are observed, the correlation between the two parameters. Then we take the different delay time distribution. So that means they predict the supernova rate as a function of color. And we, at the end, are able to have for each galaxy what is the current supernova rate, what is the supernova rate, what was the supernova rate in the past, because we have a complete knowledge, let's suppose complete knowledge of the evolution of the galaxy. Doing that, we made this plot, which is the here you have the specific star formation rate. The specific star formation rate, which means the rate per unit mass of the galaxy. And here we have the supernova rate, the models, the observations. What we see here is, first of all, there is a good overall match between the two. If we want to see difference between the different progenitor scenario, which means double degenerate wide, single degenerate, double degenerate close, we need to look to the extreme, either to the most star-forming galaxy today, or to the most passive galaxy. Here, where are the difference? At the moment, you see the dispersion point is still very large, so we cannot use that. But Rubin telescope is coming. And Rubin telescope is changing the statistics by another, possibly 2 orders of magnitude, because they predict to find 200,000 supernova 1A for redshift 0 to 1. So we say, suppose we have this, suppose that we are able to use this. Will that make a difference? So we produce this plot, which is on the top here, you have the blue line is what are the differences which we are looking at to disentangle different progenitor scenario. The green point are the current statistical errors, and the gray area are the current systematics errors. Clearly, nowadays, both systematics error and statistical error are too large to allow to separate what happens here. But these are the statistical error predicted by LST statistics. So the statistics of LST will be absolutely good enough. Now the problem go back. Yes, but can we also reduce the statistics, the systematics error? And to do that, we need to have more information of the galaxy. So to reconstruct back the star formation and so on, which is possibly, is promised as an outcome of LST. LST is not made only for transient, it's also made for galaxy, or let's say even more for galaxy. And is predicted to have colors, redshift, photometric redshift, all this data for the galaxy. So we'll have better information on a larger sample of galaxy and better statistics. So possibly we can have an handle here. is not unique, because the other thing which is going on now is the Euclid supernova search, the Euclid survey. The Euclid is not made for supernovae, unfortunately, so it does not take multiple images of the same field, and so. But there are a few exceptions. One exception is the so-called self-calibration field. It's a field which is done with very deep exposure, repeated with different frequency, not very frequent, but let's say from a couple of weeks to 1 month. 1 year ago, I tried to do a prediction how many supernovae are we expecting to see there. And these are the numbers at the end of the survey. So the things that interest me more here is that you have a good sample of supernovae redshift greater than 1, which will not come from LST. LST will stop to redshift 1 because the supernova will go too far in the red to be seen in the. So LST will, Euclid will be able to provide what we are missing from ground-based survey, and few possibly, but very important supernovae are very high redshift. I don't have a result to show here, but I only show you one of the first images which give you an hint of where you can go. On the left, you have an image from the visual camera of Euclid, and on the right, you have a ZTF current, let's say, best supernova searcher, and you see the difference in resolution, in depth, and so the promise are all there. But you may ask, where is the multi-messenger? The multi-messenger is now here. As we said, that the double degenerate system merge because of the emission of gravitational waves. The gravitational waves is going to increase in intensity as soon as they get closer and closer and closer, similar to what we have seen for the neutron star merger, with the exception that they will stop earlier because they are bigger star and they will say touch earlier, okay? They will destroy before touching anyway. So this plot shows the predicted sensitivity of different gravitational wave detectors, where here you have the Einstein telescope in green, you have LISA in red. You see where, so the supernovae, the double degenerate white dwarf are not for Einstein telescope, are certainly better from LISA, but they extend to regime where LISA is not that sensitive. And in this respect, a very fascinating project is, you have heard, I'm sure of this, is the Lunar Gravitational Wave Antenna, which was proposed by Young Arms as the GSSI. When they told to me to aim for this idea, it sounded science fiction. You are using the moon as a detector, and the moon oscillates because of a gravitational, because the white dwarf is orbiting a 10 kilo-parsec away, and they promise to be able to measure this oscillation by means of seismograph on the moon. I'm not sure if this works, but if it is, it's really fascinating. So suppose it works, we make the prediction which we will be able to see all the merging system, if existing, within the Milky Way. How many these systems are? Well, in range of frequency, how can we know? I did this simple estimate. I say, suppose that we know the rate of supernovae in the galaxy. I took this number, which comes from the most recent paper on these things. Is about 0.5 supernovae per century. So 5 supernovae per millennium, type 1a, in the galaxy. How many systems do you need to have which are approaching merging if the system is double degenerate to produce this rate of supernovae? Is 200. We see if we found 100, 200 system, okay. If not, this is not the channel. or at least this was our first approach. But if we don't find it, what happens? Well, in the literature, recent literature, there is gaining support the so-called sub-Chandrasekhar accretion to produce supernova 1A. This will increase, not that much, it will increase the pool of systems which can contribute to type 1A. So in the literature, you find often they say, well, that would be very nice. We see the merging of two white dwarfs, and then we will see a supernova. I remember these things maybe 25 years ago. Amedeo Tornabè when they say something like this, he told me, no, you don't understand anything. When the two stars become so close, it's a very complex physics which happens. The two stars destroyed. It can take a lot of time before you go from this, say, the last destroying of the star and the actual explosion. How much? Not very not clear, but up to 10,000 years or something like this. So if you don't see a supernova after emerging, unfortunately, it will not be a proof of anything. And we will. So at the present, I'm looking more than this very improbable event to the statistics. If we have 200 binary white dwarf close and with the right mass, they will produce something which explode. So this will be for the point. I want to go more quickly, very quickly actually, to a second topic, which I will not have much time. But as I say, I'm working with this with Irene Salmaso and Leonardo here, which are the strongly interacting supernovae. I will say why they are interesting in multi-messenger contest. Well, first of all, remember the first multi-messenger supernova was 87A, 25 or more years ago. There were, in that case, the detection of 2,000 neutrinos. These things is still unique. We never get another case like that. It has a lot of things. The problem is that the core collapse in the galaxy, the predicted one, are something like 2 per century. And we may need to wait another 50 years before seeing again neutrino like this of 87A. But I will not enter in this, which is there are also gravitational wave emission from the collapse of core, but let's forget this. There is another source, another kind of neutrino which are actually very much detected, are the very high energy neutrino detected by ice cube. These neutrinos are not yet very clear from what they are coming. The favorite scenario are blazar, active galactic nuclei, but the association is not so definitive. There may be, but it seems difficult that they produce all the high energy neutrinos which are found. So some people propose that high energy neutrinos can also be produced by the shock produced in supernovae when the ejecta collide with the syncostellar material. Close to the end, isn't it?
Yeah.
Diego, I'm with the time. Few or nothing. Okay, let me try to conclude. Anyway, we have indeed a class of supernovae, which I did not mention so far, which were the last, which the one which is very important is contest was discovered in 1980 with the Schmidt telescope in Asiago. It was the last supernova discovered on plates, where you had to blink the plates to find out the supernova. This was found a very unusual event, which did not show the P Cygni profile. It showed a strong hydrogen emission with multiple component, strong radio emission, strong optical emission, and also X-ray was emitted for more than 10 years. The total energy radiated was 10 to the 52 ergs, so a lot. Can these sources be produce high energy neutrino. And we set up a strategy for the PhD thesis of Irene Salmaso, which was looking to all the possibility. We search new transient inside the neutrino box, the new neutrino box, search for transient there. We study supernovae, which occurred in the neutrino box, but exploded before, because interaction will take time to set in. Quindi, is not that you get the neutrino and look for the supernova like in 87A. First, you have a supernova, and then possibly you have a neutrino. We search for correlation statistics. None of these produced, let's say, was inconclusive. And then we look at the full potential property, for physical property of potential sources, selected a few transient, find out their properties, like we need to derive the mass loss and what is the mass loss from the ejecta, what is the amount of circumstellar material which needs to be around. And I will go to the end. With this parameter, let's see if these are potential sources of neutrino. And for this, we put our measurement on this plot, which is a plot of kinetic energy versus circumstellar mass. These are regions where there are models which predict the energy of neutrino which can be produced in these events. And you see where follow the events which will follow. They follow. Some of the objects fall in a good, interesting region. Some is outside, so this will not be an interesting source, but these are interesting sources. So there is still the possibility that a fraction of the energy neutrino found by IceCube are from interacting supernovae. We need to wait for the chance to get a one-to-one association. So last, transients are in the middle of the multi-messenger era, and INAF is doing a lot of many of these components. Of course, the electromagnetic part, there are instruments especially for transient, LST, SOX, Theseus, but is also contributing to the neutrino search with the KMF, 3NET. There are two PNRR projects, one which is with the involvement on INAF, one is KMF 3NET, which is this IceCube-like, let's say, instrument, which is sorry? No, it's mainly INAF, INFN, but INAF is contributing. It is in, I say, before PNRR, INAF was not even member of this. Now we are part of this with a small contribution. These are putting IceCube-like instrument offshore in Sicily. Instead of in the ice, is in the water. Okay. Then there is the Einstein telescope, which again is the INFN projects where INAF is contributing. And there is a CTA, this case is INAF project where INF is contributing. So the transient area in the middle, and I think there is lots of do in the future. I'll stop here.
Thank you, Enrico. Are there any questions from the audience? Yes, Andrew?
Yes, except for you have provided the evidence about the fact that you need a strong statistic in observation. But my point is concerning the model that you have shown based on the data on the predicted supernova rate. If I have understood, I'm not an expert on this. For instance, people that in this model assume that there is a minimum and maximum mass. But indeed, this value depends on the statistics. You know, for instance, that the value of the minimum mass, so the maximum mass able to produce depends on the statistics.
No, it depends. What you sorry, let me ask you a question. Drop drastically. What do you mean? How much is it? Plus one plus or minus two, or
If you move from solar medallists, you the M-map value is about 7.5, so a massive depends on that. This is what we assume. But if you go at metalist around 0.003 or 4, the typical mass is around 5.5 kilometers, depends on the physics. But the difference is relevant. So it depends on the metalist. In the simulation, if I understand that, the people try to obtain indication about the transformation rate for the specific gaps. Transformation rate is a fundamental indicator, but another one is the initial mass function, and also the H that is in relation, and the impact on the mass range that you need to account for this relation. So my question is, there is someone that is working in the direction of improving this modelization?
No, definitely. You are completely right. The problem is more complicated than I was presenting. The point is, certainly the EMF is an important, not only for type 1A, but also for core collapse. The problem is that, unfortunately, I think and so this enter in when I say, what is the current systematics? So I pointed two errors, say, systematics and statistics. I still will solve the problem of statistics. I'm not sure. I do not know if we will be able to solve the problem of systematics at this point. Let's say that at the moment the people is working in two directions. One is to develop population synthesis for binary, and you know better than me that inside this there are so many free parameter that then it's very difficult to understand what is the key point, okay, at the end. If I change the common envelope scenario, what happens to the end? So we decided to follow a different approach. In principle, in our approach, we can say, okay, you tell me that there is a dependence on metallicity of 20% going from some metallicity to another for the, okay, implement that in the model and see if this make a difference. In principle, it's feasible. Is unclear if we cannot derive from first principle, let's say it will be implemented at the very end, but they can tell us if does that make a difference in the observed rate. And so, for sure, that is a place where people need to work. And unfortunately, what I see now, and let me say, it would help very much if we can have an independent characterization of the double degenerate via, say, gravitational wave. We have a completely independent distribution of parameter, and we can use, for instance, the Gaia photometry on the binaries and try to match the two things. That will be critical for the models to tune and to calibrate the model. So yes, there is a lot of works there, and new data are possibly coming. Even if we not, that's my point. Even if we do not find a supernova after the merging white dwarfs, because they will take 100 years only to wait, there is a lot to do on the statistics, on the synthesis of population, on things like that to combine the parameters.
Some questions?
May I comment? Nice to see you after a long time. When you produce that work, I spoke with Laura about and the main advantage of this approach is to cut away every other uncertainty concerning the model. But people are working with the binary populations, with this sort of varying the initial mass function, the properties of models of single cell and so on. And the difference is small. In any case, you are not able to explain what you see from observation concerning the rate. For instance, people showed that range interval there is an excess in the rate of supernova with respect to the model. Yes, but the uncertainty there is not that much. No, because it says that there are around 20 to 50 detection on supernova. So the error is large. No, in the model. In the model, I don't know able to say, but in that case, the problem is related to the efficiency of common envelope. So the interstellar revolution is no, but my consent is the following. We know that the stellar model are very large. How the evolution starts? In binary is an actor. So the point is, we arrive to a point where we'll be able to to constrain the scenario.
Look, I completely agree with you, and that's so much I agree that I was very annoyed that people who had an explanation. They don't even consider that there are stars, so they put the delay time distribution. Look, at least put inside that there are 8 solar mass stars. Will not take 4 billion years to get to white dwarf. Will take much less. So I think that yes, we need to do an effort to put as much as you can. And my point is that possibly it's better to look not to the cosmic, which was, if you look to the literature, this one was the most exploited things. Look to the cosmic evolution of the star formation rate. Here, as Piersanti was saying, you mix everything, it's very difficult to distinguish from one thing for the other. But if you look to the year and you isolate, for instance, completely passive galaxy, which were the star formation ceased few billion years ago, then you can only have one way to produce, or you select the very star forming where all the now produced supernova comes from the most massive white dwarf. In this way, with these two channels, you can possibly put some constraint which come in both directions. I want to have a constraint from the model, and I hope to provide some constraint that the model needs to implement to get to that result there. It will not be short. It takes time. We know now that when you go in detail, you cannot say, like in many papers, okay, take that. There is a problem, which is a huge problem for me. Let me show in this plot here, which is not on there, but in principle is an even more simple problem. Here, when you look to the strongly interacting supernovae, which are the most massive stars in the universe, because of this huge mass loss, so we are talking stars which are 30, 40, maybe 100 solar masses. They come all in galaxies of very low metallicity. Okay, but in the standard paradigm, the stars are losing mass because of the metallicity. These are all in systems with almost no metallicity. Okay, so they lose star in another way. Binary system, eruption of any instabilities. These things, we do not know anything. I think also that these statistics can only be explained if the EMF in these currently highly star-forming systems, however they are starting formation now, I think the EMF must be something like top-heavy. Because otherwise, you cannot have so many systems all massive. Where are the less massive core collapse? So, and there is basically no prediction from this point of view. And we are trying to get some constraint, possibly from the side of observation.
Yes, this might be a stupid question. Imagine that you can target the supernova area that is function, the galactic function, property, with the very fixed. It would provide an important constraint for the scenario.
The problem is that I cannot do that because it is the statistics will be anyway too low. Even for the supernova, it will be one every less than 1 per 1,000 years in the galaxy. Okay, for the remnants also because they don't last that much. The approach, I think, will be to select. For sometimes I was also trying to do a search of supernova in the coma cluster. Coma cluster is made almost all elliptical, very old stellar system. The problem, no one wants to do search supernova there because they are too rare. No, but having a strong, it only needs a long time, or you put together many coma-like cluster to have a rate in passive system. And I hope we can be done with the LST, where you have the full sky, finding really passive star and trying to get the rate there. That will be very interesting because you can find the tail of the distribution.
A question and a comment. The comment is quickly for SPF. There's the Nandita's paper is actually, it was based on a very heterogeneous data set. So as you know, so the H0 value that she got is kind of large, and it was in the middle. But there is a more recent paper down with the HSD data, John Blake's data.
But with Anna Marisa.
No, it's not. I mean, it's not more. It doesn't really have a, a team. And that's with SPF from HSD and near infrared. It's very, it's very much 73. Okay, it's Adam Lewis results, but it's completely independent from it. That's the comment. And I wouldn't quote actually Nandita's paper for SPF. The other comment is that figure that we were showing before. So the one with the rates and the different scenarios. So you say that we don't really know what is. I mean, no scenario for supernova progenitor is actually ruled out. So the scatter that at some point, even when you have LSST or you didn't say anything about the space telescopes, James Webb.
Not doing supernova search, really.
So, and even when we have much better data, we might have some residual scatter, statistical scatter, just because the progenitor might be just more than one. So
the progenitor might be, the two systems might come there. However, the first argument to put type 1a supernova related to white dwarf come from statistics. The very first argument, they are present also in all the stellar population. So yes, I don't think that it will be conclusive. We need to put together all the pieces from one to the other. But and statistics alone, that was why I was saying, if we have the contribution, say, from gravitational wave, you have an independent constraint, and it will work also for the Hubble tension. If you have the distance by gravitational wave, we will have another independent way, because we are missing this. A couple of years ago, I made a plot. That's actually an example of the supernova rate. It was in the night. We produced an estimate of the. It was Cappellaro, the first author, and we had an estimate of a Hubble constant, which was 74, I think, something like that. But when I show that value, I don't say we were right 20 years ago. I say, look to the error bar. The error bar is so large that it encompasses the two values that we have now. So my question with the current value of the Hubble is more, are we sure of the error bar rather than are we sure of the value? Okay. So, and the fact that there are points in between, I'm not arguing which is the better, the worse, but the error bar of Nandita was correct. In that it encompasses it needed to be. It was honest. That's need to be. And so I speak also with Anna Marisi. I must say he did a lot of works to test all the possible sources of error. So, and there is a very nice paper which is I put a reference. If you look at the paper, they say to me, look, tell me where I should look at. And I have no idea, let's say. Still, you see, I am either we want to change the cosmology, and you talk to a cosmologist and they say, no way. And so we need to be very, from our side, we need to do very suspicious of anything and try to see, look, we look to every possible thing. We cannot go down in that value. So that's my.
It's probably why we need completely independent rules.
Yes.
Maybe we can have a last question.
One question concerning the expected rate of F1As and the progenitors. Currently, it is obvious that F1As are produced by different scenarios. Probably the classical double degenerate system, at least the channel set and mass scenario is not in favor of one.
Yes, I mentioned that.
According at least to the observed chemical composition and the one expected by models. So,
I agree with you that I put this. If we do not found a system, we maybe the subchandra system works or other things. The problem is that what to say. The argument that the nucleosynthesis is not good was used 10 years or 20 years ago exactly with the reverse argument, saying no, it cannot be subchandra because the composition is not correct. So
here, the way is different. It's the opposite. I mean, and in this sense, I would like to remark that you have a delay between merging and exploding, but it is not 100 or 1,000. You have at least 6 years, 1 million years, because you have to put mass on the top of the surviving component, or you have to break the surviving component.
you mean that the single degenerate scenario cannot or not?
No, I'm speaking on the double degenerate scenario. The delay time between the merging and the explosion.
No, I was going to be much more, so I say, 10 to the 4 year. I was not talking.
No, 10 to 4 years is just the signaling phase. There is also the accretion phase.
No, I agree. So even if it is 10 to the 4, I mean, if it is above 10 to the 4,
So,
forget it for us.
so my point is that how can we correlate gravitational signal detected maybe by HWA, but also in the case we know if there is more, and they is linked to our galaxy.
Yes. Well, they don't claim that so, but let's suppose I will say yes.
Okay. So you have to select your frequency, and frequency, then we need a very close to the so very close to the match, and you can associate that then with what. There is only the possibility by path model by path model to
No. As I said, I completely agree with you. I'm not looking to correlate with supernova event. I'm looking to correlate to non-binary star. So Gaia is doing it. Certainly, I cannot do all the galaxy because it is the extinction and so on. But let's suppose that I can get to 1-2 kiloparsec. And in this 1-2 kiloparsec, going a deep survey, I can identify white dwarf that are binary systems which are detected by which are yet to go to the merging. They are maybe, and that in that case I can do a constraint on the however if they distance is 3-4 radii of the white dwarf, then they will merge. That is not. They will take time. They will merge. So that channel works. That would be my point.
yeah.
Why don't we do the discussion
Yeah.
later? Is it okay for everybody?